Hello, my name is Robin Christopher Yu, and I'm joined today by Siddhant Pansal, and we're going to discuss HyperLogLog on windowed streams. So before we go any further, we should first discuss the windowed streaming context, so we know exactly what the rules of the game are and what the problem we're trying to solve is. So in the windowed streaming context, our data comes in a stream, so we see each element in order and exactly once. It's exactly the same as the streaming context we have in class, but here we're only interested in some information about the last n elements we've seen. So not the entire stream, but only the last n elements. So for example, if we have this stream here, we might want to know the sum of it, right? The sum of all the elements in the stream. But if we get a new element, 6, then this 3 is pushed out of the range that becomes expired. And whenever we query, whenever we ask what's the sum of the elements, what we want is the sum of the elements inside this window and not outside of it. So as we add more elements will get pushed out. And so the challenge here is really to maintain some statistics about the elements inside that window. So a few metrics we might care about, of course, time complexity. How long does it take us to insert something into our window? How long does it take us to query, like the statistics over that window? And space complexity, so how much memory does it take to actually maintain this window? So you might be interested in both. Here in this talk, we'll only be concerned about space complexity. So we'll try to focus on minimizing that. Because of course there's an obvious solution for any streaming problem in this context, which you can solve in O of n times m. And the idea is just to really maintain explicitly that window size, right? So if you have n elements and each of them takes m space, then of course you'll need n times m space if you maintain everything explicitly. And in many problems, it's actually not possible to do better than linear space in terms of the number of elements. But we can do better if we are willing to settle for some approximations instead of an exact answer. And there are some problems where you can get an exact answer even with sublinear space, but we'll see those as we go along. So the problem we actually want to solve is counting the number of distinct elements inside the window. Of course, we're not going to get an exact answer, but we should get something that's reasonably close to the exact answer that we actually want. So the log-log and HyperLogLog are algorithms that were invented to solve the streaming context, this problem, but without the windows, basically. So this problem counting the number of distinct elements across all the elements we've seen. So the crucial insight behind it is really to think about a perfect hash function h that takes in an integer from 1 to r and gives an integer from 0 to n. And usually we think of this n as a power of 2 minus 1, so that the number we get is actually evenly distributed across all the binary numbers with the same number of bits. So if you think about that, then the probability that the hash contains the leading zeros to be 0 leading zeros, right, is going to be a half, because that's the probability that the binary number starts with a 1, which will happen with probability a half. And having 1 leading 0 is going to happen with a probability a quarter, and 2 leading zeros an eighth, and so on and so forth, so that having L leading zeros will actually have a probability 1 over 2 to the L. And so the idea here is to turn that insight on its head and to instead maintain the largest number of leading zeros across all the hashes we've seen to get a very rough estimate of the number of distinct elements. Right, so if you see here, this 11 has a hash of 0001100. It has 3 leading zeros in its hash, and it's the most across all the elements we've seen. And we know that we get 3 leading zeros with probability an eighth, right? So we can use that estimate and actually say that, okay, probably we've seen about 8 elements for us to be able to get something that happens with probability an eighth. And as you can see, it's actually not too far from the actual answer of 10. But you can already think of some problems, such as having a very high variance, right? Because the moment you have one bad hash, one hash that's very unlucky, and it really has a lot of zeros, and this hash can actually spoil your entire estimate. So as you can see here, if this 11 instead got hashed to 6 zeros, 6 leading zeros, then we'll actually report an estimate of 64, which is of course much bigger than the actual answer of 10. So one solution you might think is, okay, let's take some independent hashes, multiple hashes, and then just average them out. So that is possible, but of course it's costlier because we need to take multiple hashes. And we still have to ensure that these hashes are actually independent, right? So that's one way of doing things. But the way that log-log and HyperLogLog does it, it's actually very clever. And the idea they use is that they basically split the stream into multiple streams and average each of those estimates out. So what they do is they use, for example, we can use the first 2 bits of the hash, and then we determine which of the streams it should go to. So for this example, we actually split it into 4 streams, and in the first stream we have all of those numbers which hash to 00 as their first 2 numbers, first 2 digits, right? And then we solve each of these streams independently. If we ignore the 00 at the start, or the 01, if we ignore the first 2 bits at the start, then we can now actually determine the leading number of leading zeros in each of them, right? And so now you might think, okay, let's just take 2 to the 4 plus 2 to the 2 plus 2 to the 0 plus 2 to the 1. So we can do that. And that will actually give us a slightly better answer in this case. But if you look closely, it doesn't actually solve the problem of one bad hash spoiling the estimate, right? So our answer is still a pretty big overestimate. And the reason for that is, well, one bad hash, it just gets added to, it's 2 to the 4, right? So immediately we already have the scenario here where it gives more than the actual answer just by itself. So one bad hash still spoils the estimate. And you might think, okay, let's take the average of the W's first before we raise 2 to the W, right? So let's take the average and then raise 2 to that power. So that's better, because that can actually mitigate the issues of one bad hash, right? We can reduce the impact of having a bad hash. And so by doing that, we can take the average number of distinct elements for each of the streams and then multiply it by m, because we don't want the average, we want the total number of distinct elements across all the streams. And this actually works. So as you can see, the estimate now is about 13.45, which is much better. It's closer to 10, even with this 11, which hashed to a very unlucky value here. And what he described so far is actually really the crux of the log-log algorithm. But if you actually run it, if you actually implement this and run it, you'll notice that the algorithm as described still has a pretty big tendency to overestimate, right? So if you we actually ran this algorithm 1,000,000 times, right, on this case, and it gave us an average estimate of around 15.6 distinct values, which is of course much bigger than the correct value of 10, which suggests that there is some systematic error which remains even after doing that averaging. And there is in fact some systematic error, which was discovered by Flageolet and Durand when they invented this algorithm. And they discovered that by multiplying by this factor of alpha m, which is a really complicated thing here, but really by multiplying by this alpha m factor, it can actually correct that. So we won't get into the maths of how they derived this, but we can actually try it to see if it actually works. And you see that if you put alpha 4, you substitute 4 for m, and you just replace m with 4 here everywhere, and we plug this into Wolfram alpha, then you'll get an estimate of around 0.624. And you notice that if you multiply 0.624 with the average estimate we got earlier, it actually comes really close to 10, at around 9.7. So that's really close to the correct result. And of course, a footnote, the alpha m can be pretty difficult to approximate, so we have some common values of m and their approximations alpha m. And that's basically it. That's actually the log-log algorithm already. So all that does is, as we said, we initialize this W of size m. So these are the independent streams. This array W will store all those estimates of the number of leading zeros, the maximum number of leading zeros across all the elements in that stream. So whenever we see an element, we split it into the first and the front and back. The front determines which of the streams it goes to, and the back we use to count the number of leading zeros. And in the end, we just output this expression here, which we derived earlier. And if you consider the memory complexity of this algorithm, it actually turns out to be surprisingly good. It uses only m log n memory, and the reason for that is each of the m streams will store exactly one integer, the maximum number of leading zeros as we've seen so far. And this number can itself only go up to log n, right? Because if you have a number n, the number of bits it has is just log n. And so the number we're storing is at most log n. And so that means to store that number, we only need log n to store that number, right? Log n bits to store that number. So it's really good, and we have m of those, so it's m log n. And this log n is some extra, we can kind of ignore it because it just comes from computing the answer. The answer itself can have log n bits, so we can't really avoid this. But you can see this m log n is really small, so it's very good. It's very practical for large inputs. Even for very large n, it's basically a constant number. And so that's log, but HyperLogLog is essentially the same as log with a minor change to the final output. So instead of outputting this arithmetic mean we computed earlier, it actually uses this alternative, the harmonic mean. And so the intuition behind that is really just that the harmonic mean is better at ignoring outliers than the arithmetic mean. So it doesn't let outliers really affect it that much. And just changing this thing actually can reduce the error from 1.30 over square root m to around 1.04 over square root m, which is already really good. Normally we pick a reasonably large value of m, and this will tend to 0. Right. So n is usually chosen to be some sufficiently large number. Its effect on the error is negligible, because if we pick n to be really large, then it's not going to have that much impact on this error here. So we don't have n here. So the exponential histogram this one will solve the problem of this is a data structure which can solve problems on streams, right? So earlier we discussed the log and HyperLogLog algorithms that solves the problem on streams without windows. So here we can solve the problem of streams with windows, and it turns out that even some seemingly trivial problems can be pretty hard to solve efficiently when we think about it in the windowed setting. So we'll show that by actually considering this really simple problem, right? So you're given a stream of only zeros and ones, and you want to report the number of ones in the past 10 elements. Now, there's some trivial solutions you might think of, like, let's just store a counter of the number of ones. But this actually doesn't work, because if you do this, then you'll have no way of knowing whether the elements that expire are 0 or 1, right? Because you don't know what's going to expire, because you haven't stored that. And so you don't know whether you should decrease or not decrease the counter. And it turns out to solve this problem exactly, we actually need linear space. But if we settle for some answer with at most epsilon error from the real number of ones, we can actually do much better. Right. So Datar and his colleagues provided the data structure that can solve this problem and some similar problems by maintaining some special sorts of histograms, which he calls the exponential histogram. Right. And by doing this, we can actually keep the error bounded. So to illustrate this, we'll first maintain a number of buckets, and each bucket will represent the locations of contiguous segments of elements. Right. So each bucket will represent exactly one contiguous segment, and we'll only store in that segment the positions of the ones. Right. And we'll consider these positions relative to the most recent element, so that the most recent element has position 1, and then the others go 2, 3, and so on until the window size, and so on until like expired elements. Right. So in this example, this bucket 1 stores this 1 and 3 over here, stores the positions of the ones here. Bucket 2 stores these ones, and bucket 3 stores this, and this, which you can see stores some expired bucket ones as well. Now, obviously, we're not actually going to store these ones explicitly, right? Because if we can do that, then we already solved the problem. Just count how many of those ones are actually at most n. Their position is at most n. But this takes n log n space, so we can't do this explicitly. But what we can do is we can actually maintain for each bucket 2 things. Instead of all of the positions of the ones, we only maintain 2 things, which is the timestamp and the size. So the timestamp is the position of the most recent one, and the size is going to be just the number of ones in that bucket. Right? Obviously, we lose some information by doing this, but it turns out that just by storing these 2 things, we can solve the problem approximately really well. So just as an example, this bucket 3 here, 10, 11, 13, will only store 10 and the size 3, which has the number of elements in that bucket. And we can make a number of observations. So first, the observation that if the timestamp of a bucket is greater than n, then definitely all the elements in it are expired, and we can immediately just throw it away, right? Because, for example, if you have a bucket here of timestamp 11 and size 2, then we know that all of the elements, because this is the most recent one, right? All of the elements are going to be older than this 11 element. So they're definitely all expired as well. So we can just throw it away. This bucket is now useless. The second thing is that if you remove all the expired buckets, then for all the buckets except the last in terms of the timestamp, then the number of ones in that bucket is actually equal to the size. So just an example here, like bucket 1 corresponds to this 1 and this 3 here, right? And all of those are actually within your range. Similarly, this bucket 2, 5, 5, and 6 are inside the range, right? It's only bucket 3, the last bucket, which can have a problem. Because this size 3 isn't actually the number of elements that are inside the window, right? Because this 3 corresponds to 10, 11, and 13, and 2 of those are already expired. But only storing this information, we actually have no way of determining which of those elements are expired. And so using that observation, you can notice that if you have the sizes of the buckets, right, and you just report the sum of all the buckets, but for the last one, you actually report the side of the bucket over 2, then you can actually limit the error to be at most CF over 2. So the reason is because these buckets, all the buckets except the last one, definitely they're correct. But for the last one, it can have between 1 and CF elements that are actually within your window. So you can just hedge your bets and you output CF over 2. So that gives you sort of minimizes the error. It will say that the error is at most CF over 2 because again, the actual value of elements within the actual number of elements within your window is at most 1 to CF. Right. So from here, you can notice that if you can keep the size of the last bucket bounded, this actually gives you a really good estimate. So one such method to do that is to actually define K to be sort of the number of buckets that you want to have of each size. So K over 2, we use K over 2 here for the analysis, but you can think of this just as K. And the idea is we're going to store K over 2 buckets for each size and K over 2 plus 1 bucket. So basically we limit the number of buckets of each size to be between K over 2 and K over 2 plus 1. Right? So just so we run an example. So if you have K over 2 equals 1, then we have these buckets which we already produced, but let's see what happens when we add more things into this stream, right? So if we see a next element is 1, then we just add a bucket here with size 1 and timestamp 1, and of course increment the timestamps of the rest of the buckets. And when we see a next element 0, we don't do anything in terms of adding a new bucket, but we do increment all the timestamps. Now, here's the interesting thing. So when we add another element, which is 1, and we encounter a 1, we have to add a new timestamp 1 size 1 bucket. But then now we have 3 elements, 3 buckets of size 1, right? So we can't have 3 buckets of the same size because we limit between K over 2 and K over 2 plus 1, so 1 and 2. We cannot have more than 2 buckets of the same size. So we need to merge these 2 older buckets, and we just merge them by, of course, inheriting the timestamp of the smaller one and adding the sizes together, right? And we do that, and again we can continue. So next element is 0, and next element is so this is now expired. If we add another element 0, this now becomes 11, and this is expired, so we just throw it away. And so basically this is the idea of the algorithm, the data structures, just to maintain these buckets. And this is a more formal treatment of what we're actually doing, but you can pause the video to see what this is, but basically it's doing exactly what we just described. And the space complexity is actually k log squared n, because if you think about it, you have k log n buckets of each size, right? Total number of buckets is k log n. You have k buckets of each size, and they're at most log n buckets of log n sizes of the buckets. So you can have k log n buckets in total, and each of those buckets is storing log n space to store the elements. So you're gonna have k log squared n buckets space requirement in total. And if you use the tighter analysis, actually shows it's k log squared n over k. As for correctness, at least the intuition of it, you can see that by increasing k, right? If you're decreasing epsilon, then k will increase, right? Because we had the k equals 1 over epsilon. So it actually takes longer to get to the larger sizes because we have more buckets of each size. And so it's intuitively clear that when you decrease the error, when you decrease the epsilon, the error tolerance we have, and it increases k, then this decreases the size of the last bucket, which is the only thing contributing to the error anyway, right? So this will decrease the error by doing this. And we leave the formal proof to the paper, so if you want to read it, it's going to be published in a week. Of course, then you can just read the paper to see the actual proof, but the method, at least from intuition, you can see is going to give the correct answer with additive error at most epsilon. And the reason we discussed all of this is that the exponential histogram is a really good technique in general, right? So you can actually adopt it to HyperLogLog pretty directly. So if you think about HyperLogLog, right, the only thing we actually need is the maximum W for each stream. This is really the only thing we're storing. Each of those streams needs to know the W that it has in the number of leading zeros it has in that stream, right? So if we can perform windowed maximum, we're actually basically done. And so we can actually directly translate the algorithm we had previously to this scenario, where we just store the maximum in addition to all the other things we're storing. We store the maximum. And we have a lot of the nice things from earlier, like if the maximum falls within the range of all the buckets other than the last one, right, then definitely we know that the answer is correct, because this will always correspond to a complete range inside the window. It's only the last bucket which can possibly have a wrong answer, right? So this maximum 8 is actually outside the range, but these other ones, maximums, are actually inside completely. So we just store the maximums. When we add new buckets, we can merge things together, and the merging is pretty straightforward. So it's harder to do an actual tight analysis on the bounds of the error, but at least many things are promising. So if you increase k, this will tend to decrease the error, because again, only the last bucket can be wrong. So if you increase k, then the number of elements in that last bucket is going to be smaller and smaller, because the size will be smaller. So the chance that the maximum is actually there as opposed to somewhere else will be actually quite small. And of course, if the maximum is not in the last bucket, then we show that it's definitely correct, because it falls within your window. And the space complexity, for the same reason, remains the same. And in fact, if we have this, then we have already the HyperLogLog windowed version immediately as a corollary. And it's quite simple. We just replace this array W with this exponential histograms, and every time we insert something to the histogram, right, it's equivalent to this this setting of WC to be the maximum of this thing. Because normally we don't want to just store the maximum, right? Because otherwise we'll have no way to remove things. So what we're doing is, instead of setting a WC, WC is actually itself an exponential histogram, and it's gonna contain like n things, which represents n things, and those are the values that we've seen in the past n iterations. And so when we insert something to this histogram, it's just the same as inserting W prime, which is the number of leading zeros, and then inserting 0 to all the other ones. And this is quite easy to see. And to output the correct estimate is essentially equivalent to making a query on all of the WCs and then doing the estimate as earlier. And the exponential histogram, of course, dominates the memory, because we have m things, and all of those m buckets, as we saw here, this array W of size m. This is not an array anymore, but this array is actually an exponential histogram, so it requires this much space, k log squared n over k. And of course, the accuracy becomes worse, because the exponential histograms introduce more error. But it turns out there's actually a much simpler solution which doesn't introduce more error and uses more memory. So we're not going to do the analysis for the accuracy of HyperLogLog with this exponential histogram. But we're going to see that there's actually a much simpler solution for this case that doesn't introduce any more error to the HyperLogLog algorithm. So to do that, recall that W takes only values from 0 to log n. So if you just store the timestamp of the most recent occurrence of each of those values, then we actually solved the problem already, right? Because if you store only the timestamps, then if a timestamp goes bigger than n, then we know it's expired, right? And to get the maximum, we can just iterate over like 0 to log n and see which of those guys, what's the largest value in this range, which corresponds to an element that's not expired. So as a really, really simple example, if you have this scenario here, then you notice that we can actually just take this element, and we just look at the numbers here, which are the timestamps of the most recent occurrences. And this 10 actually corresponds to this guy over here, this 3, which is the most recent occurrence of the 3. But when you add another element, let's say a 2, then now this becomes 11, because we increment 1 to all of them, and this becomes 11, which is now expired. It's outside the window size, so we just replace it with this sort of garbage value to say that this is now outside of the range. And by doing this, then the space complexity becomes log n times log capital N. So n is the number of values we have to keep track of, right? Because again, we have the number of leading zeros can be 0 to log n, and this capital log n is the position on the window. So this requires capital log n bits, and of course this is much better than k log squared n because it has no dependence on k. It actually normally we need to set this k to be something reasonably large to get a good result, but here we don't need to do that because we don't have k, and even better, it gives us the exact answer all the time. So this gives us the final space complexity of m log n log capital N for the windowed HyperLogLog for a similar reason as earlier. And so that actually concludes the segment on the explanation. So we'll just go through this quickly because we don't have too much time left. We'll just go explain some application and extensions of this algorithm analysis that we did. So one of the most common applications of distinct counting in the windowed streaming setting is analyzing web traffic, right? So we can actually identify some common types of web attacks in real time if we analyze IP addresses. So one of the things we can do is actually look at the IP addresses we're getting, and if there are very few distinct hits, this could actually be a sign of a malicious actor trying to flood your server by making lots of requests. And so in this scenario, it's actually perfectly suited for the windowed setting because the Windows streaming setting, because we only care about the most recent hits. The hits from about 1 or 2 days ago are not very useful. And the window of concern can be quite large, so it's not feasible to store linear memory. We can use the algorithms we described. The sliding HyperLogLog would actually be suitable in this case. So in real applications, we'll probably want to optimize for time complexity as well as to make sure we can actually respond in real time. So we didn't analyze that here, but if we perform the operations exactly as stated, then they can be rather slow. So we'll leave this stuff to the interested reader to actually optimize for time complexity. Many of these are actually quite simple to do if you think about it for a few minutes. So we don't have to discuss all of them because we don't have too much time. And there are lots of optimizations, other optimizations you can do to increase the time complexity. So that's all I have for today. Thanks for watching. If you like this video, please make sure to like and subscribe. Leave a comment if you have any questions. And I'll see you in the next one.